Okay. Ooh. It's working? Okay. So, yeah. Okay, so to universality. Of random graphs. Okay, so first, thank you very much. It's a great honor. So as Avi mentioned, I'll talk about universality of random graphs, and this is a joint work with Asaf Ferber from MIT and Kai Lu from Harvard. So let me start with the general setting. We're in the world of random graphs, and more specifically, I'll consider the random graph model GNP. So I want to think on GNP as a random variable, takes values from the set of all labeled graphs on n vertices, and the distribution will be such that each pairs of vertices, each edge appears independently with probability p. So we have n vertices, and each edge appears independently with probability p. And p can depend on n. So perhaps the most typical question in this field is think about your favorite graph property, and now I want to ask for which values of p, g and p satisfy this property with high probability. So a typical question. So we have some graph property, and we have p. P can be, again, a function of n. So determine whether g and p satisfies this graph property with high probability. And when I say with high probability, I mean that the probability tends to 1 when n tends to infinity, because p can depend on n, of course. Okay, so usually we consider p to be a monotone increasing graph property. And by monotone increasing, I mean that if we have a graph that satisfies p, then adding more edges cannot destroy this property. So if G is a graph that satisfies p, then every other graph that contains G will also satisfy p. Okay, so regarding the main question, the typical question, what is known? So it's a famous result by Bolobash and Thomason from 87, I think. Okay, so
give examples like connectivity or
yes, of course. Yes, yes. So I have a lot of examples that I'll show later. But for example, if we want to consider a monotone increasing graph property, so containing some specific graph as a subgraph. So if I want to contain some specific graph as a subgraph, if I add more edges, it cannot destroy this property. I add more edges, maybe I contain more graphs, but I still contain this specific graph. However, if I want my graph to be bipartite, not having odd cycles, then if I add more edges, I can destroy this property. So this won't be a monotone increasing graph property. So we are interested in monotone increasing graph property. That means that we cannot destroy them by adding more edges. And what Bolobash and Thomason showed is that if we consider monotone increasing graph properties, then we have what we call a threshold probability, a threshold function for p. And what do I mean by that? So if p is monotone increasing, then there exists some function. I'll call it p star. It can depend on n, such that the probability that g and p satisfies p So I'll write it like this. So if I look at the limit, I want to think of n as a large number. If n tends to infinity, then this probability that g and p satisfies p tends to 1 if p is larger than this function, than p star, omega of p star, and 0 if p is smaller than p star. Okay, so this we call the threshold probability, or the threshold function probability.
So,
yes?
One basic question. What does it mean to be a graph property? For example, could it be a different set of graphs for every n?
Yes, yes. Okay, so when we consider G and P, it's actually a sequence of graphs, right? Because for every n, you have a growing number of graphs. And oh, you're saying about containing some graph that can be different? Yes. So for example, I'll talk about it later. But you can consider a family of graphs, and you want to contain all of them, or none of them, or one of them.
Yeah, but that's a simple example. I mean, what it means is that the property P can have very different set of graphs in it for different values of n.
Correct. Yes. So P, so of course, so the property P depends on n.
So there is no restriction on how the property is defined. Like there is no uniformity or anything.
Yes, but I want to think of the property. So the properties that I'll discuss, they depend on n. So for each, yes, I added it now. So it's not that you missed it. Yeah, so it's Pn, P depends on n. So if I sample G and P for some specific n, I'm interested in Pn, some graph property depending on the same. Correct. Okay, so thank you for.
Something has to be required. Otherwise, you could say, you know, G has at least, half inches to edges or something.
That's okay.
Correct. That's okay.
Sure. No, that's absolutely.
Yeah, I guess that's
it's just the graph property means that it does not depend on the labels of the vertices. As long as you have that, you have the Bolbach-Thomas.
Yeah.
It just says it's a property of the expansion of the Boolean cube.
Okay.
It's a relatively weak result. This little o and little omega just means asymptotically bigger, asymptotically smaller. They're much finer results.
Yes, and I'll talk about some of them. But this is something very weak but basic, that we know that we have this threshold probability. Okay, so let's indeed see some examples of this of some monotone increasing graph properties. So let us consider H to be a fixed graph. And by fixed, I mean that the number of vertices of H is not depending on n. So we have G and P. We want to think of the number of vertices of G and P as very large, and we want to consider some fixed size graph, for example, a triangle or a cycle of length 5, something which has a fixed number of vertices. Then it's known that the probability threshold for the appearance of H in G and P is n to the -1 over the maximum density of H, and by the maximum density, I mean we want to maximize the number of edges divided by the number of vertices, but we want to go over all subgraphs of H. Proper, yeah, all subgraphs of H, not necessarily proper. Okay, so if H is fixed, not depending on n, then we have the probability threshold for having a copy of H as a subgraph in G and P. Okay? Okay, so for example, what would it be for a triangle? K3. So it's just n to the -1. And it will be actually the same thing for any other, what we call a cycle. Okay, but in this example, H was fixed, not depending on n. If if I want H to be large, if I want the number of vertices of H to depend on n, or even to be what we call a spanning graph. A spanning graph is a graph that touch all the vertices of our host graph. So if we want to be H spanning graph, or we want to allow the number of vertices of H to tend to depend on n, then in this case, the probability threshold is already not that clear, and this question is much more difficult. So let's think of one example. Instead of one copy of H, because this is the probability threshold for having one copy of H, instead of one copy of H, I want to have many copies of H. I want to have a linear number of copies of H. So let me define an H factor. So an H factor of a graph G is a subgraph of G, first of all. That has as many possible copies of H which are vertex disjoint. So I want to have as many as I can copies of H. A subgraph of G with, so the number of vertices of G divided by the number of vertices of H, vertex disjoint, and copies of H. Okay, so this graph is already, it's not fixed. It depends on the number of vertices of G. And if we want to think of the rest of the vertices as isolated vertices plus some vertices. So this
example is H is an edge, and
that's just a matching, correct. So if H is an edge, then it's a matching. Actually, a perfect matching, up to one vertex at most. So perfect. Okay. Yes. Okay, so this graph is already a spanning graph. It's not a fixed graph. It depends on the number of vertices of G. And determining the threshold for this graph was much more difficult, and it took many years until Johansson, Kahn, and Wu were able to determine the threshold for an H factor. So in their paper from 2008, they showed more things, but among other things, they also found the probability threshold for an H factor. So the probability threshold for an H factor in G and P would be, okay. So what can we expect it to be? So instead of, here we need only one copy of H. But here we want a linear number of copies of H, correct? So maybe let me do some calculations here. So we wanted the number of copies of H in G and P. This time we wanted to be linear. So let's see what we can expect for. Let's look at the expectation. And the expectation of the number of copies, so H is a fixed graph. And the expectation of the number of copies is more or less n to the number of vertices. We have to divide our graph we have to choose where do we want to put the copies of H, and then we want the edges of this graph H to appear. And we want it to be linear. So it gives us something like P n to the minus V of H minus 1 divided by E of H. Okay, it gives something like this. And apparently, this is not the probability threshold for an H factor. But the probability threshold is not very far from this. So let me define. I will write D1 of H. It will be what I have there, the number of edges divided by the number of vertices minus 1. And the probability threshold for an H factor, if H is fixed, and it will be n to this, n to the -1 over d1 of H, but we must have another log factor. So log 1 over the number of edges of H times. And this will be true when H is fixed, and I also want to have one more restriction. So I want that this, we call this the one density of H. So I want the one density of H to be obtained on the entire graph and not on a subgraph. So if for every proper subgraph of H, its one density is smaller than the one density of H itself. Okay, so this is something I want to have.
So for the matching example, this D1 is 1, and you get n log n. I mean, n log n edges.
So
you need n log n edges in order to see a perfect matching.
So for the matching example, this one, yeah, exactly.
Mm-hmm. It's easy and was known and so on.
Yes, it
and
was
the
easy.
factor appears because of sort of coupon collecting.
Correct, yes.
Really,
So we,
and I guess in general.
yes, so we have to lose some log factor in order to be able to cover all the vertices. Somehow when we want to have spanning structures, so we need to have a little bit more to be able to cover everything. But again, let's see. Mm? Sorry?
Is the exponent on the log
Positive.
Positive. It's the number of edges in H.
There is a probability to be higher. Otherwise, let's say the matching example, you'll have many isolated
Vertices.
nodes, and they get like a linear fraction of isolated nodes, and you cannot fit any subgraph.
Mm-hmm. Okay, so let's indeed see some examples that I will also use later. So what is the probability threshold for a triangle factor, K3 factor? So we just have n to the -2/3 times log to the 1/3 n. Okay, we have 3 edges, 3 vertices, and this is what we have. Another example that I will use later. So instead of triangle factor, let's look on K, a complete graph factor. So K delta plus 1 factor. So this is the complete graph on delta plus 1 vertices. Its maximum degree is delta. So here we have n to the minus 2 over delta plus 1, I believe, log 1 over delta plus 1, choose 2n. No, you can see that yeah, delta plus 1. Okay. And you can see that indeed if you put delta equals 2, then we get what we have here. And another factor that I'll be interested in is the cycle factor, so CL factor. So this is a cycle of length L. And what will be the probability threshold for this? It will be n to the minus L minus 1 divided by L log 1 over L.
To simply to say that this graph CL satisfies this balance problem.
Correct. Correct. I need to say it. I mean, I should check it before I use it. And actually on some kind of so what they did, they didn't only determine the probability threshold, but they actually showed the exact probability that an H factor appears in G and P. So maybe I'll just write it. What they showed is that for every C1, there exists C2, such that if P is at least C2 P star, then G and P contains an H factor, but they know the probability. So with probability, 1 minus n to the minus C1. So if we want to get closer to 1 in the probability, we are paying by the constant here. And if we don't care about the constant, if we just want to be omega, then yeah, then we can get as close as we want, polynomially. So this was just a remark. Okay, so
For the case of fixed graph, you get better.
yes, yes. Also for the case of fixed graph, we have something better than this. But I will not need it later in my talk, so I didn't state it. I state only things that I need later. Okay, so now we talked a little bit about the monotone graph property, which is containing some graph as a subgraph. But maybe I want to ask something more general. Maybe one graph is not enough for me. Maybe I want to contain a family of graphs. Okay, so this kind of questions, we call them the universality questions. Graph is universal with respect to some family if it contains all the graphs in this family simultaneously. So this is universality. So let's define if F is some family of graphs, then G is F universal if for every member of this family, every member of this family is a subgraph of G. Okay, so now let's see a simple example. So if F is the family of a triangle and the cycle of length 4. Okay, so we have a family of 2 graphs. Then let's look at this G. Okay, this is our G. Is this graph F universal?
Triangle.
No, we don't have a triangle, right? We have C4, but we don't have a triangle. So this is not F universal, but let's look at this graph. So is this graph F universal? Yes, because we have a triangle and we have C4. And they intersect, and it's okay. I just want to have a copy of each. Okay, so this graph is F universal. Okay. But universality of such a small family, it's maybe not that interesting. And also, if we want to think of our graph G, for example, if G is the complete graph, then it's definitely not interesting, because if F is a family of graphs on at most n vertices, and G is the complete graph on n vertices, then G is F universal for every family that I can think of. So we want to consider graphs that they're sparser, and in this case, the random graph G and P will be a great candidate for us. So we want to consider the universality of G and P, and we also want to consider families F that contains much more graphs than 2. Okay, we want to consider large families F. So we want the main question we want to ask is about the universality of G and P. And we can think of families F, families of trees, families of cycles, many kinds of family. And the family that I want to consider is the family that contains all graphs on n vertices. And the only restriction I give is the maximum degree that has some specific predetermined maximum degree. So age and delta will be the family of all graphs on n vertices on n vertices with maximum degree at most delta. Okay, so I allow isolated vertices, I allow edges, I can have a very small degree also, but I want to restrict myself only to graphs with some predetermined maximum degree, which is delta. And I want to talk about the universality of this family in GNP. Okay, so maybe let's see some example of two universality. So let's look at the example we had before. So delta equals 2. The same example as before. Before it was universal. What about now? Is this graph 2 universal? So n is 6. Is this graph 2 universal? So we have a maximum degree 2. What does it mean that we have a maximum degree 2? That every connected component is either a path or a cycle. We cannot have anything else. So every connected component is either a path or a cycle. So each graph, each member of this family is actually a disjoint disjoint collection of path and cycles. And I can just think about it as vertex disjoint collection of cycles, because every path I can also close to a cycle, and this is also a member of this family. So we just need to think if we have all possible vertex disjoint collections of paths. Correct, yeah. So I do have a triangle. I do have C4, I have C5, I have C6, I have C4 with an edge. This is also a member of our family, but I don't have a triangle factor to disjoint triangles. But if I add this edge, then it's already 2 universal. Okay, so this graph is 2 universal. Or H N2, H62 universal. Okay, so let's now write it precisely instead of the example. So def a graph G is delta universal if G is, it's not def, it's a notation. If G is N2 delta universal. Okay. Okay, so the problem of determining the probability threshold for G and P to be delta universal is was studied before, and we have some partial examples. So let's see what is known. First I'll talk about 2 universality. So Kim and Lee in 2014, they show that if P is at least some constant log n divided by n to the power of 1/2, then with high probability, G and P is 2 universal. And later on, so Della Monica, Koyakawa, Redel, and Roginski.
Maybe you should say that if the probability was much less than 1/√10, it probably misses C4.
Yes, okay, so.
It's pretty close to type.
Yes, so also, okay, so I'll just say that in 2015, so they were able to show that this result also holds for every delta, which is at least 3. 1/delta. And indeed, as Avi said, this may be, in some sense, it's natural, because we know that for these values of P, every delta set, every subset of vertices of size delta in G and P with high probability has many common neighbors. So somehow we can imagine that maybe we can do one by one argument to embed this. This is just intuitively, so we can see this. But the question is if we can do better than this bound of 1 over delta. So can we do?
What I said,
okay.
If you have less than degree square root n, I mean for intuition, then yeah, you're just in a random graph. You may miss by birthday reasons. You may miss 2 people having 2 common neighbors, which is just a cycle of length 4. So
correct.
It's close to what you
Yeah, exactly. Okay, so can we do better? Okay, so for this...
So to do better, you mean just sharpen the... I mean, these are just bounds.
These are just bounds.
You want to get the P star.
I want to get the P star, exactly. I want to get the probability threshold. We have bounds from one side. This gives an upper bound on P star. And we want to know what is the real value of P star.
But you have a lower bound, which is 1 over root n, let's say, for 2.
Yes, so I have many kinds of lower bound, and now I want to consider some specific lower bound that we already saw before. So let's think, if we want to be delta universal, it means that we have to contain all members of this family. So specifically, we need to contain every member of this family, and which member of this family we already met. So we met the k delta plus 1 factor. So a k delta plus 1 factor is a member of our family. So definitely we cannot get something which is better than this. Okay, so maybe something we can hope for is to get this. So we get that the P star, or a bound for delta universality, is at least this thing that we have there. N to the minus 2 delta plus 1 log delta plus 1 choose 2 n. Okay, so this is in some sense the best thing we can hope for. And
You're right, just for delta equals 2, it's just, if we took delta to be 2, then this would be n to the minus 1 times.
it would be n to the minus 2/3. It will be this, the triangle factor. Yes, yes, exactly. Exactly. So in some sense, this is the best thing we can hope for. We cannot hope for something better because we must contain a copy of k delta plus 1 factor. And what we want to ask is it enough? So maybe once we have already a k delta plus 1 factor, then we already have everything. Maybe in some sense, the k delta plus 1 factor is the most difficult graph to get in this family. So for at least for delta equals 2, I will show now that the answer is yes. So it's enough. We get this bound. So let me state the theorem. So theorem. It's with my co-authors, so Ferber, myself, and Kai Lu. We're 2018. It wasn't published yet. Okay, so we know that there exists C, a constant, such that if P is at least the threshold for the triangle factor, some constant n to the minus 2/3 log 1/3 n, then with high probability, G and P is 2 universal.
It's actually not to what I said. So you say that if the average degree is about n to the 1/3, then we already have.
If the average degree is what? Yes. You don't need the square root.
So I guess the bound for the CL factor is only n to the minus L minus 1 over L. So I guess for L equals 4, C4, it is just n to the minus 3/4.
Yeah. For one, yeah, it was confusing the worst case.
Worst case, yeah. Okay. Okay, so we do know the universality of delta equals 2. Okay, so I gave some hint before, and I said that, so actually what we get here is that the probability threshold for having one member of this family is the same probability threshold for having all of the members of this family simultaneously, which might be quite surprising. But it's also the same probability threshold for the triangle factor. And then we can ask ourselves, perhaps the reason for having this threshold is the existence of the triangle factor in our graph. Maybe if we forbid triangle factor in our family, or maybe we forbid triangles at all, then maybe we can get some better bound than what we have here. And this is the second part of the theorem. So if we take H, L, and delta to be a subfamily of our family, but containing only cycles of length at least L. We don't want to have triangles. We don't want to have any short cycles. So cycles of length at most L, at least L. Sorry, we want to forbid short cycles. So in this case, we can actually get a better bound. So if P is at least some constant. So can someone guess what the bound will be? It's on the board. The cycle factor, correct. N to the minus L minus 1 over L times log 1 over Ln. Then with high probability, G and P is H, L, and delta universal. And this is, as I mentioned before, exactly the same threshold for having a CL factor. So in some sense, the CL factor is the reason for having this threshold.
And is it a general principle that the member of your family with the largest number of connected components will always be the hardest? Because
I wish we knew.
that's the intuition, I guess.
Yes, that's the intuition, and this is also the conjecture. And maybe the next question is, okay, these theorems are good for delta equals 2. What happens for the rest of the delta? So we don't know. There are some partial results. So a very recent paper by Asaf Ferber and Raikon and Adov, they considered delta at least 3, and they were able to beat this bound, but they don't have the probability threshold yet. So they were able to show that if P is at least some constant log n over n to the 1 over delta, they save something, delta minus 1 half, but they lose something in the log. Then with high probability, G and P is delta universal. So this is the best known thing for delta universality at the moment, for general delta. Yes, so in some sense, these universality problems are not settled yet, delta universality at least, and perhaps the reason for the difficulty is that the number, or one of the reasons for the difficulty, is that this family is actually huge. The number of graphs in this family is exponential in n. So sometimes, or maybe a naive approach will be, let's choose some member of this family, prove that it exists in G and P with high probability, with some really high probability, and then just use the union bound. But since the number of members in this family is so large, is exponential in n, then it will not beat the union bound. So we actually need to have some different approach in order to prove universality. And the only known result at the moment for delta universality is for delta equals 2.
The second theorem is delta equal to 2?
Yes. Thank you. I wish it was. Yes. Here also, delta equals to 2. Thank you. Delta equals to 2. Otherwise, this didn't make any sense. Okay, so maybe it's a good time for questions or more questions. I don't know. And if not, then I'll say something about the proof. Okay, so as I mentioned before, some difficulty we have is that the number of elements in our family is too big. We cannot use the union bound. But then we can start with doing something much simpler. And we say, OK, so let's not prove universality of this family. Let's prove universality of some smaller family. Let's consider only small part of this family and start with proving universality for this. So this will be the first step, or the first phase of our proof. So we consider HL N2K will be a subfamily of our family. And here I allow only cycles of length at most k. So cycles of length at most k. And when I say, so we know it's a collection of cycles and paths. When I say cycles, I also mean paths.
Why do you use L? You're not proving the first part of the thing?
It will be the same proof.
If it's the same, then it's better to have simpler.
Yeah. OK. So it will be cycles of bounded length. So let's start with this. Let's start with proving universality of this family. So the good thing about this family is that the number of elements in this family is only polynomial in n. OK, we can think of all of the options. We have k is some constant. OK, so k is some constant. And so we allow only constant size cycles. And the number of elements in this family is actually smaller. So how do we prove universality of this family? So for Johansson-Kahn-Vu.
Yeah.
Exactly. This is what I will do. I will use the Johansson-Kahn-Vu. How I will use the Johansson-Kahn-Vu, since we have only a constant number of possible cycles, then I have one specific cycle that appear a linear number of times. Okay, so there exists L. So if we take H, let's take H from this family. So there exists some cycle such that the number of these cycles is at least n over k, or linear. Doesn't really matter what.
That is some number less than k. Yeah, that's okay. When you say there exists L, it's L some number.
Yeah. Yeah, of course. Yes, of course. We can L is less than k, of course. OK, so the number of L cycle, we have some specific cycle which appears linear number of times. So what we will do, we will actually first embed all the other cycles that are not of size L. And then in the rest of the vertices, we will just use Johansson-Kahn-Vu and show that there exists a CL factor. So first, OK, so we start with exposing. We will expose our graph G and P slowly, part by part. Each time we will add some more probabilities. So we start with Gn, let's say P over 4. It doesn't really matter. Okay, we start with exposing edges with probability P over 4. And then we embed all cycles. We embed H without all the CLs gridly. And in the second step, we expose more edges. And we look at this linear number of vertices that we didn't embed any cycles on yet. And we still have the random graph properties because it's still a linear size set. So we can actually use Johansson-Kahn-Vu. So Johansson-Kahn-Vu gives us CL factor. And we're done. OK, so for this length of cycles, we're good. for this subfamily. So now we have to consider graphs with long cycles. And for this, I will need some key lemma. It's called the connecting lemma. Okay, so the connecting lemma is based by an idea of Richard Montgomery. He used it to for different questions, but okay, so unfortunately we needed some different version of the connecting lemma and maybe some more sophisticated, so we had to reprove it, but the idea is really more or less the same. So what is the idea? We have a graph G, and we have some set of special vertices x, y, x, I, y, I, some pairs, t pairs of special vertices, and we know that we have some expansion properties. I don't want to say exactly which expansion properties I need, but some expansion properties. So G, I would say, expands into the vertices of G minus these special vertices. And again, I don't want to say precisely what do I mean by expand, but in general, I want to have sets of large sets to have many neighbors in this set, in W. We call it W. We want to have large sets to have many neighbors in W, and we want to have two large sets to have an edge between them. Okay?
So T we should think of as linear. What should we think of? T constant or linear? The number of pairs?
The number of pairs. It will work with many values of T, but we should think of T as, yeah, so I don't want to say at the moment because I will need it for different purposes. So when I get to it in the proof, I'll say precisely which T we're taking. Okay, so what do we have? So if we look at this special, and what else do we need? So we need that the xi's are all different and the yi's are all different, but xi can be the same as yi. This is okay. Okay, just want them to be all different and them to be all different. So what do we have? So let's look at the sets of special vertices, x1 up to xt, y1 up to yt. Maybe they intersect. I don't know. And I have the rest of the vertices, w. So I know that I can find, if I have the correct expansion properties, that I can find vertex disjoint path. By vertex disjoint, besides maybe the endpoints, because maybe they intersect, I can find vertex disjoint path, connecting each xi to its yi, to its pair, to its pair, in such a way that this path covers w. And they actually also have the same length. So there exists xi, yi path covering w. Okay, so I will not.
So this is an expansion property that you will expect from your random graph.
Exactly. This will be, but okay, so this lemma is deterministic. It doesn't involve any probabilistic argument, but these expansion properties I will get from the random graph. I will prove that I will have these expansion properties, and then I could use this connecting lemma deterministically. And let's, so now we can move to the second phase. So in the second phase, I want to allow, yes?
Sorry, just slightly confused about the
Yes.
So what is the conclusion of the connecting? What are you assuming? You're assuming you can, given what kind of a G, you can always find X and Y?
Yes.
Sets? Okay.
No, Given a G and a set of special vertices inside G, I can always find the path that connect a collection of paths for every I.
Okay, so what are you assuming about G?
Some expansion properties that I will get from.
Okay, you really haven't specified that.
I haven't specified it.
Okay.
I'm assuming some expansion properties, good expansion properties, and by that I mean that every large enough set have a lot of neighbors. Every two sets has a neighbor between them, but yes. Okay. So let's move to the second phase. I want to allow now long cycles. Because I proved the universality of much smaller family, I want to prove the universality of our family. So I want to allow long cycles, but I want to allow, I want that the number of vertices in long cycles will actually be large enough so I can use the connecting lemma. Let me show how it's being done. So H1 will be all the graphs in H and 2, such that I'll write it like this. So xt will be the number of CT cycles. So these are the number of vertices in cycles of size t, of length t. So if I sum over all cycles of length at most k, so this is the number of vertices in cycles of length at most k. I want it to be at most 1 minus 1 over k n. Okay, I allow it to be large, but not that large. Okay, so what do I get? I get that the number of vertices in long cycles by long I mean longer than k, is linear. Okay, so what would I do? I will take a member of this family, and let me show you how I embed one member first. So for a member of this family, I want to consider the graph SH. So SH will be just H minus the long cycles. So deleting the edges of the long cycles, minus the edges of long cycles. So SH is actually a member of the family over there. So we already embedded SH. So this is, we already had it in H and to k. So we already embedded H. So now we just need to take care of the long cycles. So we use some more, we expose some more edges in our graph. We haven't used all the probability that we can use. So we expose now some Gn p over 4. And now we have, okay, so what do we know? We know that we have still to embed the long cycles, and we have linear number of vertices that belong to long cycles. So the set that we want to have the long cycles in has a linear size. So I will have the correct expansion properties. So look at the set, at the subset or the subgraph of isolated vertices. It has linear size, and it will have the expansion properties. So here, I want to use the connecting lemma. So how I will do this? So I have many vertices that somehow I want to connect to have cycles. So I will choose special vertices here. Of course, I need to make sure how I choose t, as you asked before, and how I choose the special vertices. But then I will call this x1, x2, x3, xl, and this will be y1, y2, y3, yl, or y4. And assume that 4 is linear or very large. And then I will use the connecting lemma to connect xi to yi. So I'm using the connecting lemma to connect xy to yi to create a cycle. And I do it simultaneously for everyone. And then I create the long cycles. Okay, so this I did using the connecting lemma and the expansion properties because I had enough vertices in long cycles. Because I had linear number of vertices in long cycles,
So enough is used in the fact that actually P gets smaller when it's restricted to this subset of isolated vertices.
Yes.
Right, because most of the edges of
Yes.
constant factor will go. So effectively, P is dropping by a factor of 8.
P.
From the set of isolated vertices, you have much sparser set of edges.
Correct. Yes. 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 So, but I really used here the fact that I have many vertices on long cycles, and now I still need to take care of maybe the most difficult part of the proof, which is vertices. We have some long cycles, but not many vertices are lying in them. Oh, you can also ask me, okay, you showed us how to embed one member, right? But you said before that the union bound will not work here. What do you do with everything else? So actually here, the union bound will work. Why? Because the number of SH is polynomial in N. And for each SH, I have many different ages. So I will have a very huge set of graphs H that will give me the same SH. So this bounded to be polynomial in N. And then the rest of the vertices, the set of the isolated vertices, it will be linear in N. And I will show the expansion properties of this set. So I just need to choose the set of special vertices. How many special vertices can I have? At most N. Right? Because I cannot have more special vertices than the size of my graph. Okay, so in total, when I union bound here using this technique, then I have to union bound over at most n to the k plus 1. And this I can do. Exponential I cannot do, but this polynomial I can do. So I embedded one member, but using this connecting lemma, I can actually use the union bound.
This argument is there ever a reason not to use k equals 4 or something? Keep it a parameter in the whole
Yes, yes. K will need to be large. Yeah, it needs to be large. Yeah. Okay. So I just need to do the difficult part now. But I will just give the idea. So H2 is everything else. So it's Hn2 minus H1 and Hn2k. Okay, so I have long cycles, but not many vertices in them. So not many vertices in long cycles. So why is it a problem? Assume that I have a graph. I have a huge triangle factor and one cycle of size log n. So using this technique, first I embed the triangle factor. I embedded it already here. And now I have a set of isolated vertices of size log n. I want somehow to create a big cycle, but I cannot expect to have expansion properties in a set of size log n, or maybe even smaller in GNP. Okay? It will actually be probably empty. Correct. So I cannot use this. So if I have huge triangle factor and one cycle of size log n, I cannot use this. So I want to still use what we already embedded in the first phase, and the idea will be as follows. So maybe I don't have many vertices in long cycles, but it means that I do have many vertices in short cycles. Correct? So there exist many vertices in short cycles. So let's say at least n over k, correct? Yeah, sorry. Correct. So I have many vertices in short cycles. And what matters is it's linear in n. So again, I can find some specific cycle that appears a linear number of times. So there exists L such that the number of CL, L is smaller than K, the number of CL, again, is linear in n. Let's write just theta of n. Okay, so now instead of SH, I will take SH star, which will be SH. Okay, so I deleted the edges from long cycles, and instead of them, I add as many copies of CL as possible. So many CL copies, as much as possible. So maybe I have some isolated vertices, but not many. So now I have a graph which doesn't contain log cycles. So it's in our family that we embedded before. And I just need to tell you how do I create from this graph the graph that I want. And the union bound will work the same thing as there, so we don't have to worry about the union bound here. Oh. I knew it will happen at some point.
No, the people who are really cool go to the corner there, and there are special devices to pick up the...
Okay, we will measure my coolness after my talk. Okay, so how do I take this graph and make it to be my original graph? So first, I already have this graph. And now I want to look only at the SL cycles, at the SL copies, because the rest I already embedded, I'm fine with it. So assume that L is 4, just for the picture. I have many C4s. I don't want to take triangles, because then it will be difficult to explain, but easier to prove. Okay, so assume I have C4s, and now I want to expose more edges. So I'm using my last expansion. So again, P over 4, I have enough edge probability. I expose the rest. And I have some edges now between them. I exposed new edges. So the new edges, let's make them green. I have some edges between them, correct? And I will define some auxiliary graph, and the graph will be as follows. Every CL cycle will be a vertex. And in every CL cycle, I will choose some special edge. Just an edge, no matter how you choose it. Arbitrary edge. And for each edge, I will set the start and the end, right? So let's call it S and T for this special edge. And I will connect the vertex here with the vertex here if they're corresponding cycles. If in the corresponding cycle, I have a green edge between S and T, and I will direct it. So if I have an edge between S and T, then I will have, in these two cycles, then I will have a directed edge from this vertex to this vertex. And I will keep doing it. And note that if I have a cycle in this graph, then I can actually come back to my original graph and have, so I have S to T. I can do like this, S to T, assume I can do like this. I have S to T. like this. Okay, so if I found a directed cycle in this graph, I can come back to my original graph and open it to a cycle. So I want just to find a way to find long cycles in this graph with the correct parameters. They will give me the correct length of cycles that I'm looking for. But so how do I do this? So actually, I have linear number of CLs. So I have linear number of vertices here. And I will have the expansion properties in this graph, because I have the expansion properties in this graph. So I can prove also expansion properties of this graph. So I need to use some more sophisticated version of the connecting lemma. I need it to be directed connecting lemma. OK, so we prove some more sophisticated version of the connecting lemma. We just need it to be directed. And we do the same trick as before. We want to close cycles, only directed cycles now. OK, so we have the directed cycles. We go back here. Using the connecting lemma, another version of the connecting lemma, we go back here. We have the cycles that we wanted, and we still have many CLs left. But this is OK, because we need to have many CLs in our original graph. And that's it. That's the main idea. So I know I just waved hands here in the last part, but this is maybe the main idea. So just maybe I will state the most obvious open problem. So is delta universality in general. So for delta at least 3. So the conjecture is that it should be the same as into universality. We should be able to determine the probability threshold to be the same as the k delta plus 1 factor. So the conjecture is that the probability threshold for delta universality is the same as the probability threshold for k delta plus 1 factor. And this is still open. And maybe more approachable problem will be, instead of looking at the family H and delta, so these graphs are spanning, which is very difficult. Maybe we can do some subfamilies of this family and consider only almost spanning. So H 1 minus epsilon and delta. OK, so there are some results. I will not state them now. There are actually many results regarding this family, but still we don't know the probability threshold here. So maybe this will be more approachable. But
even for delta equals 3, you don't know?
Even for delta equals 3, there are some results. I think it's up to maybe a log 5. They know more for delta equals 3, but definitely not for every delta. Maybe it's more approachable. I cannot promise this. OK, I'm done.